that involves gases, sometimes it will be beneficial for us to use our ideal gas law, as we said, to help us figure out the answer. So here we've got the reaction for the synthesis of methanol. Okay, and the question asks, what volume of hydrogen do I need to synthesize 35.7 grams of methanol? Okay, so what we're going to do is we are going to figure out how many moles of hydrogen we need by going from grams of methanol to moles, moles of methanol to moles of hydrogen. Okay, then using our PV equals nRT ideal gas law, we can figure out volume. Okay, so let's get started. 35.7 grams of methanol. If you calculate the molar mass of methanol, you'll find that in 1 mole we've got 32.04 grams. And if we go to our balanced chemical equation, we can see that 1 mole of methanol is produced from 2 moles of hydrogen. So this is moles of methanol. 1 mole of methanol. 2 moles of hydrogen. Moles of methanol cancel out. Grams of methanol cancel out. That's going to give us 2.23 moles of hydrogen. Okay, so now we're going to solve for volume from our ideal gas law and RT over P. Okay, so we've got temperature in Kelvin, we've got pressure in torr. So of course we're going to need to multiply this by 1 atmosphere over 760 torr. That's going to give us 0.971 atmospheres. And then I think we've got what we need. We know that we have 2.23 moles of hydrogen times our ideal gas law constant, 0.8206 liters atmospheres per mole Kelvin, times our temperature, 355 Kelvin. Take all that and divide it by our pressure, which is 0.971 atmospheres. Atmospheres cancel out, moles cancel out, Kelvin cancel out, and we're left with liters. That's a good thing. And if you throw this into your calculator, multiply everything on top, divide it by 0.971, we get 66.9 liters. Okay. So the last thing we're going to do is take a look at the a little bit of the molecular side. We're going to take some of our information about gases and look at it from a molecular standpoint, and generally this is known as kinetic molecular theory. And there's just a few tenets of the model of gases from kinetic molecular theory. Some of them we've described previously, and such that temperature is a relative measure of kinetic energy. So higher temperature, higher kinetic energy, higher kinetic energy, higher temperature. 2, the volume or size of gases are negligibly small. And so that's this tenet is sort of the reason why all gases, the mole volume, is 22.4 liters. 22.4 liters is a large volume, and so the ratio of the volume of that the molecules or atoms of gas occupy relative to the entire molecule will not change much if you go from a small atom such as neon to a bigger atom such as argon. 22.4 liters just dwarfs the size of the gas, so that doesn't make a dent in the volume. And the third tenet is that gas molecule collisions are elastic, meaning that they do not lose energy from the collision. Inelastic collisions transfer some of the energy to lose some of the energy due to friction, other things like that, and those are, of course, elastic. So, gas molecule collisions are inelastic, or excuse me, they are elastic, meaning that they do not lose energy to the collision. Okay, most of the ramifications that we're going to talk about from kinetic molecular theory deal with the fact that temperature is a measure of kinetic energy. Okay, so you can see that implications of kinetic molecular theory that as temperature goes up, the kinetic energy goes up. And since we know that one of the equations for kinetic energy is 1/2 mv squared, what this implies is that as the kinetic energy goes up for a molecule, what that means is that the velocity is increasing. They're moving faster because, of course, if you're looking at the same gas, the mass is going to be constant. So here we have the distributions of velocity for nitrogen at various temperatures. And notice that we do have to say that it is a distribution. At a given temperature, not all of the nitrogen molecules have the exact same kinetic energy and therefore that exact same velocity. They have a distribution, and actually it's called a Boltzmann distribution. So as the temperature increases from 273 to 1000 Kelvin, the distribution of velocities increases, meaning that a majority of the molecules are moving faster. And the average kinetic energy and the average velocity of the molecules is also increasing, which you can calculate using the root mean squared averaging technique. And if you increase the temperature to 2000 kelvins, the distribution increases as well. So as temperature increases, the velocity of the molecules increase. Okay? What would happen if we take a look at several different gases at the same temperature? How would their velocities differ? Well, if we have different gases at the same temperature, that means same temperature means kinetic energy is going to stay the same. And so what would happen if the masses vary? Well, this would give us information about the velocity. And it turns out that if we take a look at that, you can see that the lighter gases move faster at the same temperature. And we can look at this as a function of kinetic energy equals 1/2 mv squared, the equation. You can see that if all of these gases are at the same temperature, same nominal kinetic energy, you can see that as the mass goes down, the velocity must go up to keep kinetic energy constant. And so that's why the velocity of gases increases as we go to smaller molecules. Oxygen, the heaviest molecule here, has the lowest distribution of velocities. Hydrogen, the lightest gas, has the highest distribution of velocities. So as the molecular weight increases, the velocity of molecules goes down at constant T. So as the molecular weight goes down, velocity goes up. Okay, a couple of definitions that we should also discuss when we talk about the velocity and motion of individual gas molecules. And that would be diffusion and mean free path. Okay, so it turns out that because gas molecules are moving so fast, if they're in a closed container, there is a sort of not a straight line going from point A to point B, because they of course can collide with each other. And the distance in which they travel before hitting other gas molecules is the mean free path. So even though gas molecule is moving very, very fast, as we saw in these plots, we could have looked at these thousands of meters per second. You know that if you spray perfume at one end of the room, it takes not a long time, but a longer time than you would expect. If this molecule can move 1,500 meters per second, it should be at the back of the room within a microsecond. But of course, it takes much longer for, say, the vapor from perfume to travel that distance, because as they're moving from one end of the room to another, they're going to bounce off molecules, bounce off other molecules, and finally get to the other side of the room. Okay, this is known as diffusion, the rate at which molecules can fill a space. Okay, another definition for gas molecules is effusion, which is the rate at which molecules will leave a container into a vacuum through a small hole. Okay, so this is proportional to the molecular weight of the molecules, because of course, as the or inversely proportional, effusion is inversely proportional to the molecular weight of the molecules, because of course they would be moving slower at that point in time. Okay, so far all we've discussed is ideal gases, and so what we've done is we've sort of assumed a couple of things. The fact that we've assumed that the effect of intermolecular forces is small, and it turns out that that is the case at higher temperatures and higher pressures. But at lower temperatures and lower pressures, the attraction between molecules or atoms of a gas can start to decrease their pressure. Okay, so what we can see here is the plot of pressure as a function of temperature for an ideal gas in the red line, and xenon for the green line, or real gas. You can see that the calculation from PV equals nRT for the red line starts to deviate at as you decrease pressure and volume. And what intermolecular forces again are, the attraction between xenon molecules. And so what happens if you have a surface, say a xenon balloon? Okay, we know that the pressure is a measure of how much force that xenon molecule is going to exert on the inside of that force. If you have another xenon molecule near it, there is intermolecular force attraction towards it. So what that can do is that can reduce the pressure in which it strikes the force, or this is sort of a simple analogy for this phenomenon, and it can lower the pressure than what should be calculated. The next assumption that we've made is that the size of the gas molecules is small relative to its container. And that, of course, is going to be true, except at really, really small pressures or really, really high pressures. Really, really small volumes or high pressures, I wanted to say. Okay, so what we have is that at smaller pressures, smaller volumes, higher pressures, the size of the individual gas molecule starts to be an appreciable amount relative to the volume of its container. So the size of the molecule will start to impact the size and pressure that you're measuring. So again, the red line is what we calculated using the ideal gas law, and the green line is actual data. So you can see that it's not until 200 atmospheres, 200 times atmospheric pressure, where the real gas, as these are referred to, starts to deviate from the ideal gas law, but it nonetheless does occur. Now for both of these non-ideal behavior or real gases, effective intermolecular